Okay, so now we're going to look at this problem, which is I guess it's a first order advection equation type thing. It's just not written that way. It's written as a function of two spatial variables. Sorry, my mic's in the wrong spot. It's written as a function of two spatial variables. We're going to solve this by method of characteristics. So the first thing we're going to do is we're going to assume that one variable is a function of the other. Right, so in this case, I'm going to say let x equal x of y. So we're sort of parameterizing in terms of y. Now we can use the chain rule, right? Because that means now u is just a function of y. U is just a function of one variable y, like this. So we can use the chain rule to figure out what the derivative of u with respect to y is. So total derivative, right? So this is an ordinary derivative, right? Is du dy partial plus dx dy ordinary, because x is a function of y only, du dx. So that's the chain rule. What we note is that this looks like this looks like this. So if those two things are equal, if dy dx equals a, then du dy equals this expression here and is equal to 0. If dx dy equals a, du dy equals 0. Now this implies that, or what we'll start putting some terminology on this. We call this the characteristics. This defines the characteristics. This is true upon the characteristics. So essentially, a characteristic's like a line. In this case, it's a pretty easy line to determine, that we slide along, and that's how we access our solution. So this means that upon the characteristics, u is constant, right? Because we can just integrate this with respect to y. U equals some constant c. Constant upon the characteristics. Now this is very important. The reason that's very important is because it says that the initial condition must be constant, right? So when I started out here, I didn't actually set an initial condition. I just started playing around with it. However, I'm sure if I look back in the problem, I will see an initial condition. Let's look at what this equation implies about our characteristics. So let's integrate both sides with respect to y. X naught. Okay, so that's a straight line. You can rearrange it to be something like x over a minus x naught. Right, so what you've got, x, y, you've got characteristics that look like this. Right? Everywhere the slope is 1 over a. And these represent, the starting points represent different values of x0. So let's go and read the problem again and check out what our initial condition is. If we don't have one stated in the problem, we'll just have to assume. According to the solution in front of me, I assumed or was given the initial condition. At y0, we've got some function of x. So because it's constant along the characteristics, we know that always this line here, let's draw a big arrow down here, because we're constant on the characteristics, u of xy equals u x on the characteristics equals f of x on the characteristics x naught upon the characteristics, right? We really wind this function right back to the starting point of the characteristics. What we do know is that all the characteristics are defined by their starting point x naught. We know x naught as a function of x and y. So in fact, what we have off the characteristics, or to get off this characteristic type idea, we just want to substitute at x naught, because that's our definition of the that defines our characteristic. So what we have is we have this sort of sliding coordinate. As our x changes or our y changes, this pulse, this f of x, just sort of carries on, just like some sort of pulse thing, right? So you can think of this as, you know, C like a wave equation. So that's your initial f of x, or f, that's your initial f. It'll propagate with speed a in the y direction. Or as y increases. That might be a better way of putting it.